Hello students, and welcome to section 9-3, Rewriting Radical Expressions. So to jump in here with example 1, we'll use properties to rewrite radical expressions for part A. How can you visually show that the square root of 16 is equivalent to 2 times the square root of 4? So let's take a look. As it shows here, we've got a depiction of a square system or grid. It does say draw squares using grid paper that have side lengths equal to the two radicals. Now, I don't necessarily think that you need to have grid paper to understand it, but it does work out if you do have it, that you can set it up to where each one of these squares is a representation of a 1 by 1, let's say, and then 1, 2, 3, 4 of those squares combined by another 1, 2, 3, 4 of those squares, a total of 16 squares, as you can see, represent this larger square. The square root of 16 ends up being, as you can see, 1, 2, 3, 4 of those squares, and those side lengths add up to, of course, simply 4. As it turns out, with this smaller square, of which has 1, 2, 3, 4 inside, one of these is the square root of 4 as they're representing, or 1, 2. It turns out the square root of 4 is in fact 2. Similarly, the same with this. You've got 1, 2, the square root of 4 being just that 1 and 2. So it turns out you can represent it as a kind of sum, as it turns out, wherein the sum of the lengths of the two smaller red lines is equal to the length of the larger red line. So the square root of 16, quite literally the length, which of course is 4, is equal to this square root of 4, which is 2, plus again the square root of 4, which is 2. As it turns out, you can rewrite this as root 4 plus root 4, or 2 root 4. How can you compare the square root of 20 and 2 root 5? The product of square roots states that the square root of AB is equal to the square root of A times the square root of B separately. Notice that they've kind of pulled out, so to speak, each respective part. So there's the root A, that radicand on its own, separate from that radicand, as you see, root B. Again, when both A and B are greater than or equal to 0, this will hold true. We're going to use properties of square roots to show an equivalent expression for the square root of 20. And as we're about to see, writing root 20 as a product of square roots takes shape as such. So we do know that obviously 20 being the product of 4 times 5, and they've already split it up, as you can see, with root A times root B up above with that property. The square root of 4 times the square root of 5. Again, two separate roots, two separate radicands. A perfect square factor of 20 happens to be 4. So in the next step, they wrote 4 as such, 2 times 2, which is smart because then in the next step, the square root of that ends up being simply 2. And then you're left with the square root of 5. And that on its own, then, 2 root 5 is your final answer. Therefore, the radical expression, square root of 20, is equivalent to 2 root 5. Example 2. Write equivalent radical expressions. So what is an equivalent expression for the square root of 63? Let's take a look. Square root of 63, well, they first started as rewriting the radicand of 63 as 9 times 7. It does say write a factorization of 63 using as many perfect squares as possible. Speaking of which, and speaking of simplification, I guess, in the next step, 9 simplifies as such, as you can see, 3 times 3. It is a perfect square, so they write it as you see. The square root of 7, there's nothing more that can be done with that particular radicand, so you leave it. And of course, the square root of 9, and because you've got, again, the same number here essentially being multiplied, the square root of 9 then in turn just becomes that 3. 3 root 7 is your final answer, so the equivalent expression to the square root of 63 is just that, 3 root 7. All right, example 3. Write equivalent radical expressions with variables. What is an equivalent expression for the square root of 63x to the 9th power? Turns out, like we've seen already with at least 63, you can rewrite that. Let's continue though. An x to the 9th also can possibly be manipulated. However, there'll be maybe some extra nuances with the variable. Rewrite the expressions to remove perfect square factors in the radicand. Remember, this whole quantity under the root, including the expression x to the 9th, is technically the entire radicand. Turns out you can in fact break up 63 into 9 times 7, and then from there rewrite x to the 9th as they describe here as a product of x to the 4th, x to the 4th, and x. And the reason that is nice is because x to the 4th and x to the 4th are identical, right? These two actually pair together if you remember properties in the past wherein you can add exponents and that becomes x to the 8th. Okay? X to the 8th is a perfect square, so to speak, in the context of expressions, variable expressions, that is. So these two end up, because they're the same, end up being part of this solution when you take the square root of x to the 8th. All right, so the next step, there you have it. We're putting it all together in the context of one big radical still. And then you can split it up. The square root of 3 times 3 under one radical, square root of 7 under another, and then lastly you've got these two as algebraic expressions with variables as you see, x to the 4th times x to the 4th times square root of x. These two comprise to be 9, which is a perfect square. These two comprise to be x to the 8th, which is a perfect square. The square root of which ends up being 3 for this particular root, and here x to the 4th. The square root of 7 and the square root of x stand alone under the root. There's nothing more that can be done. So the equivalent expression of that starting root, the square root of 63x to the 9th, is in fact 3x to the 4th times the square root of 7x. Example 4. How can you write an expression for the product of 3 root 5x times 2 root 15x cubed without any perfect square factors in the radicand? Well, as it turns out, one of the properties we've already discussed when it comes to splitting up roots also applies to bringing them together, so to speak. The product, as you'll see here in a moment, finding the product will demand just that, bringing them together. So here's the original problem, and as it states, using the product property of square roots to multiply the radicands, you can literally pull in 5x under one root along with 15x cubed. 3 times 2 stay out of the radical, which we can easily do, of course, in a moment we will. But these we do have to manipulate a bit more, of course. So let's take a look. It turns out you can break up 15 into 5 times 3. This 5 stays as is. The x cubed times x, they wrote as x to the 4th, which is, I believe, just as good, if not better than the broken up version of the prior step, because you can easily break it up in the next step as, because it's a perfect square, as x squared times x squared. And look, in the next step, they've also rewritten one root here as 5 times 5, a root here as a standalone, which you can't do much more with, root 3. But again, x squared times x squared is x to the 4th. Because it's a perfect square, it's nicely going to be conveyed as such so that you can actually take the square root in the next step. Rewrite to show the perfect square factors, of course. And there's the next step. Square root of 5 times 5, or square root of 25, technically is 5. Square root of x to the 4th, or x squared times x squared, is just x squared. The root 3 is alone, as you can see. It can't be simplified. And of course 3 times 2, earlier we got 6 all the way down there. So the final answer multiplying through 30 x squared root 3. The equivalent expression to this original problem, of course, is just that. Example 5. Write a radical expression. A light fixture in an ice cream shop is in the shape of an ice cream cone, and the cone has a height that is 7 times the radius. The expression for the slant height, which is right here in the picture, if you look at this picture, it's I would argue a clear depiction of a triangle, how they have highlighted it. The slant height is written as this, the square root of r squared plus h squared, where r is the radius. In this case, you can see already in the depiction of 3 inches. And h is the height of the cone, which they represent here from top to bottom, essentially. The slant height should be no longer than 24 inches to fit on the wall. What is the slant height of the cone with the radius shown? Okay, so again, here's the expression. We also have this parameter, a height that is 7 times the radius. So how do we put this all together with the information? Let's start to formulate. Let r equal a radius and 7r be the height. As again, they had described here. The height is 7 times the radius. So h equals 7r. Okay. As you can see then in the next step, again, the square root of r squared plus h squared will be our primary tool for doing the analysis, the expression at least. In this particular case, in this particular step, you can see how they've substituted 7r in for h. Because again, that's what we described earlier as we set up that first step. So 7r is equal to h. So now look at this expression. This expression is a representation of a typical algebraic expression that we can actually simplify because of the nature of, well, 7r squared, as you see in the next step, that's 49r squared. Again, it says substitute the values, which you've already done. And then in the next step, because we have like terms, r squared plus 49r squared ends up being 50r squared. Okay, and that particular radicand we can manipulate here by virtue of breaking down the factors of 50. 50 is 5 times 2. And embedded in those factors, you see 5 times 5, which ends up being, of course, a perfect square, the square root of which is 5. And the r squared also ends up being a perfect square. R times r, if we think of it that way, the square root of which, of course, is just r. So the expression, right, the expression as we're seeing put together using all of those components, 5r times the square root of 2. Again, that's our slant height. To determine the slant height of the cone, evaluate the expression as they again described r to be equal to 3. Because r is equal to 3, we can plug it in. We've got 5 times 3, and then again we have a root, so root 2. Now, the answer won't be particularly nice because root 2 is irrational. It's a non-fraction, or a number you can't write as a fraction technically. So if you type this onto your calculator, you get 15 root 2, in other words, to be 21.2. So the slant height is about 21 inches, so it will fit on the wall. How do we know that? Well, again, the slant height should be no longer than 24 inches. So this dimension right here, this slant height, because it ended up being 21.2, 21.2 is less than 24, so we know that it'll fit. Okay. In satisfying some of these other questions, as usual, if you'd like to try it, particularly the try it problem at the bottom, if you want to try it, please do so. We will most certainly talk more about all of these nuances with radicals when we're together.